Welcome to the lesson on sensor working principles. Upon completion of this lesson, learners will be able to describe how sensors work, describe the closed-loop sensor control system, and explain how fundamental electrical principles enable sensors to convert physical phenomena into measurable electrical signals. Let us start by describing robot sensors. These are essential components that convert physical energy, such as light, heat, or force, into electrical signals. Sensors enable robots to perceive their environment, which is critical for achieving autonomous operation. By providing vital input data, sensors ensure the safe and accurate operation of robotic systems. They create output signals that let robots interact with the physical world. This flowchart illustrates a basic example of a robot equipped with two sensors. These could be color sensors or proximity sensors, any device that provides the robot with information about its surroundings and influences its behavior. The first decision point in the flowchart involves the robot's two sensors. If either sensor detects the color black, the robot is instructed to back up or reverse. This demonstrates how sensor data, combined with an algorithm, translates into specific actions. To illustrate this concept, consider a Roomba-type vacuuming robot. It might have two sensors on its underside to detect the presence of a floor surface beneath it. If both sensors detect black, indicating no floor or a significant drop, the robot is programmed to reverse to prevent falling downstairs. Similarly, if one sensor detects a drop while the other does not, the robot might turn away from or toward the drop depending on its programmed behavior. Finally, if both sensors confirm the presence of a floor surface beneath the robot, it proceeds forward in its current direction. Robots use sensors and encoders in various locations to control movement and positioning. Sensors can be embedded in different parts of the robot to collect data. These locations are strategically chosen based on what the robot needs to monitor. The movement of these sensors depends on signals sent to an encoder. This communication ensures precise control and coordination of the robot's actions. The encoder then calculates these signals to determine the robot's next steps. This real-time processing allows the robot to adjust its movements based on the environment and tasks. A sensor control system is fundamentally designed to maintain precise control through continuous feedback and adjustment. It operates as a closed-loop system that enables constant monitoring and modification of the process, bridging the gap between digital and analog domains. While computers process information using digital signals, the physical processes and their corresponding sensors operate with analog signals, necessitating conversion between these two formats. A critical parameter in these systems is the sampling rate, which defines the number of samples taken per second. The relationship between sampling rate and system performance is direct. A higher sampling rate leads to increased precision and sensitivity of the sensor, allowing for more accurate control of the process. The closed-loop system flowchart illustrated here can be better understood with examples as we proceed through this lesson. Let's use a robotic arm's position control system as a practical example. Imagine a robotic arm that needs to move precisely to pick up objects. Here's how the control system works, explained in 8 steps. The process begins with a digital reference input, which specifies the desired position for the robotic arm. In this case, the system receives specific coordinate instructions, such as moving to position 30 centimeters in X, 20 centimeters in Y, and 15 centimeters in Z direction. These coordinates are represented as digital values that the system can process and understand. The digital computer acts as the brain of the operation. It performs complex calculations to determine the exact motor movements required to achieve the desired position. The computer runs control algorithms that calculate the necessary power for each joint motor, ensuring the movement will be smooth and precise. These calculations take into account various factors like speed, acceleration, and the arm's current position. The third step is digital to analog conversion. This converter bridges the gap between the digital and physical worlds. It takes the computer's digital instructions and transforms them into analog voltage signals that the physical components can use. For instance, when the computer specifies a 180-degree rotation, the converter might translate this into a corresponding 5-volt signal that the motors can understand and execute. The actuator system consists of electric motors positioned at each joint of the robotic arm. These motors respond to the analog voltage signals they receive. The voltage level directly influences the motor's behavior. Higher voltages result in more powerful or faster movements, while lower voltages produce gentler, more controlled motions. These motors are the physical devices that actually create the movement of the arm. The process step represents the actual physical movement of the robotic arm in real space. During this step, the arm moves according to the actuator's commands, attempting to reach the specified position. This is where the digital instructions finally get converted to real-world mechanical motion. The next step is where the measurement sensors continuously monitor the arm's actual position using encoders installed at each joint. These sensors produce analog signals based on the physical position of the arm. For example, they might detect that the arm is currently at 29.8 centimeters in X, 20.1 centimeters in Y, and 15.2 centimeters in Z direction, providing feedback about how close the arm is to its intended position. Next is the analog to digital conversion. This converter takes the analog readings from the sensors and converts them back into digital values that the computer can process. For example, a 4.9-volt signal from a position sensor might be converted into a digital reading of 178 degrees. This conversion is essential for the computer to understand and process the feedback information. The feedback system, marked as number 8, completes the control cycle by returning position information to the computer. The computer constantly compares the actual position, like 29.8 centimeters, with the desired position of 30 centimeters and calculates necessary adjustments. This comparison and adjustment process happens many times per second, allowing the system to make continuous refinements until the actual position matches the desired position precisely. This video demonstrates the use of sensors in robotics. Importantly, sensors can be located on board the robot, off board the robot, or both. They enable robots to perform various tasks, including locating parts, creating parts, and interacting with objects. For example, this video displays the use of an off-board vision sensor. Positioned above the robot, this sensor captures an image of the part the robot will interact with. This image provides information about the part's orientation, enabling the robot to determine the appropriate motion and path. Simultaneously, an onboard pressure sensor monitors the robot's interaction with the part. This sensor detects when the robot encounters resistance, indicating contact with the part. It also signals the completion of the task when the resistance diminishes, signifying the removal of the burrs. Let us now explore the basic sensing mechanisms that rely on fundamental electrical principles to function. The first type is resistive sensors, which operate by measuring changes in electrical resistance when exposed to external stimuli. Next are capacitive sensors, which detect variations by measuring changes in capacitance as objects interact with their electric field. The third type is inductive sensors, which function by measuring changes in inductance when metallic objects affect their magnetic field. To understand sensing mechanisms, we will first review 3 key electrical concepts that make sensor operation possible. Resistance is the opposition a material offers to the flow of electric current, and it is measured in ohms. Capacitance represents a system's ability to store electrical charge when a voltage is applied, with measurements taken in farads. Inductance is the property of an electrical conductor to oppose changes in current flow by storing energy in a magnetic field, and it is measured in henries. These fundamental electrical principles form the basis for different types of sensors and their operation. First, we have resistive sensors. As the name implies, these sensors measure changes in electrical resistance. A key advantage of resistive sensors is their compatibility with both AC and DC power sources, as resistance remains consistent for both. Resistive sensors offer fast response times due to the instantaneous nature of resistance changes. They also exhibit a wide operational range, allowing for the measurement of various physical phenomena, such as temperature changes or mechanical displacements, by adjusting the desired resistance range. A significant benefit of resistive sensor design lies in the controllability of resistance values. To minimize power consumption, high-resistance sensors can be employed. Conversely, lower resistance values, typically in the hundreds or thousands of ohms, can be used when power consumption is less critical. Resistive sensors, like many other sensor types, can be remotely operated and mounted, contributing to the overall autonomy of the system. The image displays a sensor that measures distance using light beams and special lenses. When the light bounces off the target and returns to the sensor, it changes the electrical resistance inside the detector, much like a light sensor in your phone that adjusts its resistance based on how bright or dark it is. This changing resistance helps the sensor calculate the exact distance by converting light signals into electrical measurements that the control unit can process. The second type is the capacitive sensing principle. As the name implies, these sensors operate based on changes in capacitance. Capacitive sensors are highly sensitive, like resistive sensors. However, the sensitivity of a capacitive sensor depends on its construction and the associated circuitry, such as AC to DC converters. A significant advantage of capacitive sensors is their low power consumption. Unlike resistive sensors, which inherently involve current flow, capacitive sensors primarily measure changes in capacitance requiring minimal current. The diagram demonstrates two equivalent configurations of a capacitive sensor, one showing two separate plates with areas A separated by distances D1 and D2, and another showing the equivalent single capacitor with the same plate areas and a total separation distance of D1 plus D2, where the blue section represents a dielectric material. The sensor functions by creating an electric field between these plates, and when an object approaches or touches the sensing area, it alters the effective dielectric properties, thereby changing the capacitance between the plates. This change is then detected and converted into a useful signal. Common application of capacitive sensors include measurement of pressure, touch, and proximity sensing. Capacitive sensors measure changes in capacitance, which can be achieved through three primary mechanisms: change in overlapping area, change in distance, and change in dielectric material. Let's look at the change in overlapping area. As the overlapping area between two capacitive plates increases, the capacitance increases. Conversely, decreasing the overlapping area by sliding the plates parallel to each other reduces capacitance. This is evident in the capacitance equations, where the overlapping area is directly proportional to capacitance. Next, we will look at the change in distance. The capacitance is inversely proportional to the distance between the plates. Increasing the distance between the plates decreases capacitance, while decreasing the distance increases capacitance. The last change is the change in dielectric. The second equation demonstrates the influence of the dielectric material on capacitance. Introducing a material with different dielectric properties between the plates alters the capacitance value. For example, inserting a dielectric material into the space between two plates in air will result in a change in capacitance. Capacitive sensors can be constructed in various forms, such as flat plates or cylindrical configurations, depending on the specific application. By manipulating these three factors, overlapping area, distance, and dielectric material, capacitive sensors can be used for various purposes, including on-off detection and proximity sensing by monitoring changes in distance or overlapping area. The third principle is the inductive sensing principle. Inductive sensors are devices that operate on electromagnetic principles to detect metallic objects. These sensors work by measuring changes in inductance while creating an electromagnetic field that detects the presence of metallic objects through variations in the magnetic field. Their non-contact operation ensures extended life and reliability in industrial environments where dirt, dust, and moisture are present. While they are limited to detecting only metallic objects, with detection ranges varying based on target material, they excel in industrial applications due to their fast response times and high repeatability, making them particularly suitable for speed and position sensing in manufacturing applications. The diagrams illustrate the physical significance of three key parameters in inductance: permeability, reluctance, and the number of coils. Permeability refers to the ability of a material to support the formation of a magnetic field within itself. In the image, the core material influences the magnetic field. Changes in the core material, such as the insertion or removal of an iron core, alter the permeability and consequently the inductance. The second image depicts reluctance, which represents the opposition to the flow of magnetic flux within the magnetic circuit. The air gap in the diagram contributes significantly to reluctance. As the air gap increases, the reluctance increases, hindering the magnetic field's ease of flow through the loop. Conversely, decreasing the air gap reduces reluctance. The image on the right depicts the number of coils. The number of turns in the coil directly impacts inductance. Increasing the number of coils strengthens the magnetic field and consequently increases inductance. These parameters can be manipulated to design sensors with specific sensitivities and operational characteristics. For example, varying the number of coils allows for adjustments to the sensor's response. Let's now look at how the parameters permeability, reluctance, and cross-sectional of coils influence inductance and discuss the different types of inductance sensors, namely self-inductance sensors, mutual inductance sensors, eddy current sensors. Self-inductance sensors utilize a single coil and measure changes in voltage across it. A primary mechanism for change in self-inductance is the variation of the medium's permeability. For example, moving an iron bar through the center of the coil alters the permeability within the coil, resulting in a change in the output voltage. This is evident in the self-inductance equation, where a change in permeability, mu, directly impacts the inductance value. Other factors that can influence self-inductance include the number of turns of the coil, N, coil length L, and cross-sectional area, A. By measuring the voltage at different points along the coil, we can effectively vary the number of coils and observe changes in inductance. While typically fixed, the effective length of the coil can sometimes be adjusted to influence inductance. Next is mutual inductance sensors. These sensors employ two coils, primary and secondary, and measure the voltage change across secondary coil due to changes in the magnetic field generated by the primary coil. L1 and L2 in the equation are self-inductances of the two coils. Factors influencing mutual inductance include the relative position of coils, also known as coupling factor K, changes in the primary coil current. Changes in the distance or orientation between the two coils alter the magnetic coupling and consequently the induced voltage. Any change in current or magnetic field in the primary coil induces a voltage in the secondary coil. Next, we have the eddy current sensors. These sensors detect changes in current, often induced by external magnetic fields. For example, moving a magnet near a conductive material like an iron bar within or near the coil induces eddy currents within the material. These eddy currents, in turn, generate a magnetic field that interacts with the sensor coil, resulting in a measurable change in inductance. Lastly, we have the handheld metal detectors. These devices are the best examples of eddy current sensors. As the detector sweeps across a surface, it generates a magnetic field. When the detector encounters a metal object, eddy currents are induced within the object. These currents generate their own magnetic field, which interacts with the detector's internal coil, causing a change in inductance that is detected and displayed. In summary, sensors operate on the fundamental principle of converting physical energy into electrical signals, enabling the measurement and monitoring of various physical phenomena. These electrical signals can be generated through changes in three key electrical properties: resistance, capacitance, or inductance. Resistance can be manipulated by altering the length, cross-sectional area, or temperature of the resistor. Similarly, capacitance variations can be achieved by modifying the distance between plates, the plate area, or the dielectric medium. In the case of inductance, changes can be implemented by adjusting the coil length, cross-sectional area, number of turns, or the permeability of the medium. Thank you.